In order to provide a correct description of the behavior of von der Waals gases in a thermodynamic state within the unstable region of the pressure versus volume diagram, James Clerk Maxwell, the famous Scottish physicist and mathematician, introduced a graphical method called Maxwell construction to identify the boundary points on isotherms that correspond to saturated phases of the gas or liquid. Maxwell started with the observation about the general assumption on the homogeneity of medium in a vessel. If a phase transformation of the medium must be taken account, then we cannot expect that its spatial distribution remains homogeneous, and it may be in completely different thermodynamic states during liquefaction or vaporization. If we consider an isotherm of a von der Waals gas at the temperature less than the critical temperature in the pressure versus volume diagram, and pinpoint different thermodynamic states on it from the state A to the state G with the states C and E at the local maximum and the local minimum of the isotherm, then we can see that the pressure of the medium in the states B and F is the same, but its volume and density are very different. Here the states B, D, and F are chosen such that the system has the same pressure. Maxwell assumed that the medium may evolve directly from the state B to the state F along a horizontal isobaric path instead of passing through the intermediate states C, D, and E. In this way, a gas or vapor is liquefied along the isobaric path between the rarefied state B and the fully condensed state F, and the isotherm of the medium is represented by the broken curve A, B, D, F, and G. When Maxwell constructed this broken curve isotherm replacing the original one derived from the solution of the von der Waals equation, he used the following arguments. If one is able to prevent the saturated vapor from condensation, the medium can also be brought from the state B to the state C along the green curve. Similarly, by carefully keeping the liquefied medium from contact with vapor and preserving it in the liquid condition, the medium may also be brought from the state F to the state E along the green curve. However, the red curve C, D, and E represents unstable states where the isothermal compressibility of the substance is negative. These states cannot therefore be realized, and as Maxwell put it, this curve must be handled only as a hypothetical path in the pressure versus volume diagram representing the physical states of the medium. Then he considered a closed hypothetical path where the medium passes from the state B to the state F along the curve B, C, D, E, and F while staying homogeneous, and returns to the state B along the horizontal isobaric line between F and B as a liquid-vapor mixture. Because the curve B, C, D, E, and F is a part of an isotherm and the temperature does not change along the horizontal path between the states F and B during vaporization, the temperature is constant in the whole process. As a result, no heat can be converted into pressure-volume work during the thermodynamic cycle. The pressure-volume work done in the process is given by the total area of the closed curves F, D, E, and B, C, D in the pressure versus volume diagram, where the sign of the area is determined by the direction of the path along which the system evolves. The total area representing the work is then the area of the closed curve F, D, E, minus the area of the closed curve B, C, D, which must vanish as no net work is done in the isothermal process. This tells us that the areas of the closed curves F, D, E, and B, C, D must be the same, and the Maxwell construction applies it as a criterion to determine the boundaries of the phase transitions represented by the states B and F on the isotherms of a von der Waals gas. By identifying these points, a part of the isotherm between the points B and F, including the unstable branch between the points C and D, can be replaced by the isobaric horizontal line connecting the points B and F. As already mentioned, this means that any isotherm of von der Waals gases below the critical temperature is replaced by the isotherm represented by the broken curve passing through the points A, B, D, F and G determined for each isotherm. If we use the graphical method determining the equal areas of the closed curves for the unstable branches of these isotherms, then each of them can be replaced by an improved isotherm where a horizontal line represents the unstable region of phase transition in the pressure versus volume diagram. We note that the region of instability covers a smaller area in the diagram than the region where the phase transition takes place, and their boundaries only meet in the critical point K. When we describe the different branches of an improved isotherm based on the phases of matter evolving along the isotherm, we can state the following. The isotherm between the states A and B describe the thermodynamic state of medium, when it is an overheated vapor. If the medium is in the state B, then we talk about a dry, saturated vapor of low density which is about to condense or liquefy. The isotherm between the states B and F is the stage of the vapor-liquid phase transition of the medium along the horizontal branch at constant pressure. In the state F, the medium is already completely liquefied and it is called saturated liquid of high density. If we reverse the direction of the evolution of the medium along the isotherm, then F denotes the state where the saturated liquid is at boiling point and is about to vaporize. After presenting Maxwell's arguments for the graphical method, we discuss how to apply them for a real thermodynamic system, for example a gas in the measuring cell of a critical point apparatus. Here the system is the medium in the measuring cell, and its surroundings consist of the water chamber containing the cell with the thermostat serving as a heat bath, and the mechanics changing the volume of the cell. Let us consider the reversible isothermal thermodynamic cycle for the medium along the closed path B, C, D, E, F, D and be used in the Maxwell construction. This cycle is hypothetical in the sense that it passes through the unstable states along the curve C, D, E, and it is a quasi-static reversible process where there is no entropy production. We can apply the first law of thermodynamics for the medium in the measuring cell, stating that the infinitesimal amount of heat Q absorbed from or released to the heat bath by the system is equal to the infinitesimal change in its internal energy U, plus the pressure P of the medium times the infinitesimal increase or decrease in the volume V of the cell. We integrate this equation over the closed path, where we determine the contribution of each term to the change in the state variables of the system in the thermodynamic cycle. Because the system has returned into its initial state, the total change in its internal energy U is equal to 0, that is the cyclic integral of the internal energy vanishes. Then the total heat exchanged between the medium in the cell and the water chamber is equal to the cyclic integral of its pressure P with respect to its volume V. At the same time, no entropy is generated in the system during the reversible cycle, and the differential of the entropy S of the system integrated along the closed path vanishes. By applying the definition of entropy, we can write the left-hand side as the cyclic integral of 1 over the absolute temperature T of the medium with respect to the heat Q exchanged between the system and its surroundings. Since the cycle is isothermal, the right-hand side is equal to 1 over the temperature T times the total heat exchanged between the medium and the heat bath during the cycle. If we substitute the result obtained from the first law into this equation, we will have 1 over T of the cyclic integral of P with respect to V, which must be equal to 0. The cyclic integral of the pressure with respect to the volume describes the pressure volume work done on the medium in the measuring cell by the mechanical part of the apparatus compressing the medium, or on a mechanics by the expanding medium. We note that the mechanics only allows the gas to expand if the volume of the cell is changed by the hand wheel of the apparatus. Then the result tells us that the pressure volume work done by or on the system vanishes, where we can break up the path into two branches along which the integration is performed. The first integral is computed along the closed curve B, C, D, B, and the second one along the closed curve D, E, F, D. The sum of these integrals must be equal to 0. By changing the direction of the integration in the second term, we can write that the integral of the pressure with respect to the volume along the closed curve B, C, D, B is equal to the integral of the pressure with respect to the volume along the closed curve D, F, E, D. Because these integrals in the pressure versus volume diagram of the medium are given by the areas of the closed paths along which the integrals are computed, we conclude that the areas enclosed by these two curves must be equal. Here the states C and E are determined by the isotherm for a given temperature, and the task is to find the states B and F, which also determine the state D by evaluating the equal areas of the two closed paths of the thermodynamic cycle. The most straightforward method to find the equal areas is the usage of a fine grid on the pressure volume diagram, where the cells covered by the areas of the two closed curves can be counted. By using a trial and error method, the difference between the counts determined for both the areas must vanish for the proper choice of the boundary points. Evidently this method has a limited accuracy, and nowadays various numerical methods are applied for the Maxwell construction. They normally include some combination of numerical integration schemes and root-finding algorithms with iterative techniques. There are several different ways to do Maxwell construction, and we show here a simple method to determine the boundary volumes of the phase transition of the medium based on the equal areas for an isotherm at a given temperature. We saw that the pressure P of a von der Waals gas is given by the gas constant R times its temperature T over the difference between its molar volume Vm and its volume correction constant B, minus its pressure correction constant A over Vm squared. The vanishing partial derivative of the pressure P with respect to the molar volume Vm at a constant temperature T can be used to determine the local maximum and the local minimum of any isotherm at temperatures lower than the critical temperature of the gas. This condition gives the equation stating that minus R times T over the square of the difference between Vm and B, plus 2 times A over Vm cubed is equal to 0, and two of its roots are the molar volumes V sub mc and V sub me of the gas at the local extrema of the isotherm. We will use these molar volumes as a starting point to find the boundaries of the phase transition. In order to compute the area in the pressure-volume diagram equivalent to the pressure-volume work for an isothermal process, we will evaluate the integral of the pressure with respect to the molar volume between the minimum and maximum molar volumes occupied by the gas during its evolution. For example, the area under the isotherm between the molar volumes V sub mf and V sub md is given by the integral of the pressure P with respect to the molar volume Vm with the lower and upper limits V sub mf and V sub md. If we insert the pressure of the von der Waals gas into this expression, and perform the integration, then we need to evaluate the primitive function given by the natural logarithm of R times T over the difference between Vm and B, plus A over Vm. This gives the natural logarithm of the ratio of V sub mf minus B to V sub md minus B, plus A over V sub md, minus A over V sub mf. The rule of the equal areas tells us that the areas of the closed curves DEFD, and BCDB must be equal in the Maxwell construction. The area of the first closed curve can be obtained by subtracting the area under the isotherm from the rectangle with the base given by V sub md minus V sub mf and with the height given by the pressure P' of the medium in the states B, D and F. Then this area is equal to P' times the difference between V sub md minus V sub mf, minus the natural logarithm of the ratio of V sub mf minus B to V sub md minus B, minus A over V sub md, plus A over V sub mf. This expression must also be equal to the area of the second closed curve, which is given by the difference between the area under the isotherm and the area of the rectangle with the base Vm sub B minus Vm sub D and the height P'. That is, the right-hand side of the equation can be written as the natural logarithm of the ratio of V sub md minus B to V sub mb minus B, plus A over V sub mb, minus A over V sub md, minus P' times the difference between V sub mb and V sub md. After simplifying this equation, we obtain the condition telling us that the pressure P' times the difference between V sub mb and V sub mf, minus the natural logarithm of the ratio of V sub mf minus B to V sub mb minus B, minus A over V sub mb, plus A over V sub mf must vanish. We use this condition to find the molar volumes V sub mb and V sub mf, where the pressure P' is determined by the evaluation of the von der Waals equation at any of these molar volumes. As an initial guess in the method finding the molar volumes, we can choose the average Vm bar of the molar volumes at the local maximum and minimum of the isotherm, which can be substituted into the von der Waals equation providing the initial pressure P bar of the numerical procedure. If we insert the pressure P bar into the von der Waals equation and solve it for the molar volume, then we obtain the other two roots V sub mb bar and V sub mf bar besides the root Vm bar, which can be used as the initial boundaries of the phase transition in the procedure. We also have the condition stating that the pressure P of the medium at the actual values of the molar volumes V sub mb and V sub mf must be equal, and apply it as the first equation to solve. Again, the pressure in these states is denoted by P'. The second equation of the system is the equation of equal areas, and the system of these two equations can be solved by applying some iterative method for finding the roots V sub mb and V sub mf, that is the molar volumes for the boundary points of the isotherm that correspond to the saturated phases of the medium. An alternative method for determining the boundary volumes of the phase transition of a medium is based on the Gibbs criterion using the Gibbs potential or the chemical potential in the Maxwell construction. When we studied thermodynamic potentials, we established that an infinitesimal change in the free enthalpy or the Gibbs potential G of a thermodynamic system is equal to minus the entropy S of the system times the differential of its temperature T, plus the volume V of the system times the differential of its pressure P. In the case of isothermal processes, this equation reduces to the relation stating that the differential of the free enthalpy is given by the volume times the differential of the pressure. Let us integrate this relation over an isothermal path from an initial state A to an arbitrary state. Then we can express the Gibbs potential G of the system as a function of the constant temperature T and the instantaneous pressure P, and write it as the initial Gibbs potential of the system in the state A, plus the integral of the volume V of the system with respect to the pressure from the pressure PA in the state A to the pressure P. Since we integrate the volume of the system with respect to the pressure, we show the molar volume versus pressure diagram for one isotherm of a von der Waals gas at the temperature less than its critical temperature, where the states B and F are the boundary states of its phase transition, and the states C and E are the states where the isotherm has the local maximum and the local minimum in the pressure versus volume diagram. Then the change of the free enthalpy G of the system evolving, for example, between the two states A and B, can simply be written as the integral of the volume V of the system with respect to the pressure P from the pressure PA of the system in the state A to the pressure PB of the system in the state B. We obtain a similar relation by applying the Gibbs-Duhem equation for a one-component system, which states that the number of molecules N in the system times the differential of the chemical potential μ of the system, is equal to minus the entropy S of the system times the differential of its temperature T, plus the volume V of the system times the differential of its pressure P. Here the number of molecules N is given by the amount of species N times the Avogadro's number Na, whereas the chemical potential μ can be expressed as the partial derivative of the Gibbs potential G with respect to the number of molecules N at constant temperature and pressure. Again, for an isothermal process the Gibbs-Duhem equation reduces to the relation stating that N times the differential of μ is equal to V times the differential of P. This shows that the change in the Gibbs potential is given by the number of the molecules in the system times the change in its chemical potential, and the usage of the free enthalpy and the chemical potential is equivalent in this problem. As a result, the differential of the chemical potential μ is given by 1 over the Avogadro's number Na, times the molar volume Vm of the system times the differential of the pressure P. This equation can be integrated along an isothermal path from the initial state A to an arbitrary state as in the case of the Gibbs potential, which gives an equation stating that the chemical potential μ as a function at the constant temperature T and the instantaneous pressure P of the system, is equal to the initial chemical potential of the system in the state A, plus 1 over the Avogadro's number times the integral of the molar volume Vm of the system with respect to the pressure from the pressure Pa to the pressure P. Then the change in the chemical potential μ of the system evolving between the two states A and B can simply be written as 1 over the Avogadro's number, times the integral of the molar volume Vm of the system with respect to the pressure P from the pressure Pa to the pressure Pb. Now we use the equations describing the change in the free enthalpy or the chemical potential of a medium to introduce the Gibbs condition selecting the boundary states B and F corresponding the saturated phases of the medium. This condition states that the Gibbs potential G of any substance must be the same in the boundary states B and F of its phase transition. Or equivalently, the chemical potential μ of the medium in the state B must be equal to the chemical potential in the state F. If we compute the change in the free enthalpy and the chemical potential between the states B and F by applying the two integrals obtained here and insert these conditions into the result, then we can state that the integral of the molar volume Vm of a medium with respect to the pressure P from the pressure Pb to the pressure Pf must vanish during the phase transition of the substance between the states B and F. For the change in the Gibbs potential we just substituted the volume V by the amount of species N times the molar volume Vm in the integral. The figure shows that the system evolving along the von der Waals isotherm between the boundary states of the phase transition must pass through the states C, D, and E. As a result, we can break up the vanishing integral from the state B to the state F to the integrals between the state B and the state C, between the state C and the state D, between the state D and the state E, and between the state E and the state F. By reversing the direction of the integration between the states C and D, and between the states D and E, we obtain the equation stating that the integral of the molar volume Vm with respect to the pressure P from the pressure Pb to the pressure Pc, minus the integral of the molar volume Vm with respect to the pressure P from the pressure Pd to the pressure Pc, is equal to the integral of the molar volume Vm with respect to the pressure P from the pressure Pe to the pressure Pd, minus the integral of the molar volume Vm with respect to the pressure P from the pressure Pe to the pressure Pf. Here we see that the first integral in the left-hand side of the equation gives the area under the isotherm between the states B and C, and the second integral gives the area under the isotherm between the states C and D. Their difference is equal to the area of the closed curve B, C, D, and B. Similarly, the first integral in the right-hand side of the equation gives the area under the isotherm between the states E and D, and the second integral gives the area under the isotherm between the states E and F. Their difference is equal to the area of the closed curve D, E, F, and D. Now we can conclude that the Gibbs condition selects the boundary states B and F for the phase transition of the medium such that the areas of these closed curves in the volume versus pressure diagram must be equal. We therefore obtain the same criterion of the equal areas derived for the pressure versus volume diagram of the von der Waals isotherms by Maxwell, that is, the application of the Gibbs criterion is equivalent to the Maxwell construction. However, the volume or the molar volume Vm of the medium as a function of the pressure P and the temperature T is a cubic equation which is an implicit function of the pressure at a constant temperature. This expression is more difficult to integrate than the pressure expressed in an explicit form as a function of volume. Fortunately, the change in the Gibbs potential can be monitored during the phase transition, which helps us to find the boundary points corresponding the saturated states of the medium on the von der Waals isotherms. In order to examine the region of the phase transition in the volume versus pressure diagram for von der Waals gases, we will derive the explicit form of their Gibbs potential. We have already seen that the differential of the free enthalpy G of a gas in an isothermal process is given by the volume V of the gas times the differential of its pressure P. We can formally divide this expression by the differential of the volume V, and write the partial derivative of the free enthalpy G with respect to the volume V at a constant temperature T, as the volume V times the partial derivative of the pressure P with respect to the volume V at a constant temperature T. If we express the left-hand side of this equation in terms of the molar volume Vm of the gas, and integrate it with respect to Vm from the molar volume in an initial state A to the molar volume in an arbitrary state, we obtain the Gibbs potential as a function of the pressure P at a constant temperature T. The right-hand side of the equation can also be written in terms of the molar volume Vm. If we insert the von der Waals equation into this form and calculate its derivative with respect to the molar volume at a constant temperature, then we obtain Vm times the sum of minus the gas constant R times the temperature T over the square of the difference between Vm and the volume correction constant B, and 2 times the pressure correction constant A over the cube of Vm. By removing the brackets we obtain minus R times T over the difference between Vm and B, minus R times T times B over the square of the difference between Vm and B, plus 2 times A over Vm squared. If we integrate this equation with respect to the molar volume between V sub Ma and Vm, then we obtain the primitive function minus R times T times the natural logarithm of the difference between Vm and B, plus R times T times B over the difference between Vm and B, minus 2 times A over Vm, which has to be evaluated at the upper and lower limits of the integral. As a result, the change in the Gibbs potential G of a system evolving from the state A is given by minus the amount of species n of the medium in the system, times the gas constant R times the temperature T, times the natural logarithm of the difference between the molar volume Vm and the constant B, plus n times R times T times B over the difference between Vm and B, minus 2 times n times A over Vm. This form can be used to determine the free enthalpy of a von der Waals gas along its isotherms passing through the unstable region. Equivalently, one can use the chemical potential μ for the same purpose, since the Gibbs potential in the case is just the product of the number of molecules and the chemical potential. In the molar volume versus pressure diagram we have chosen an isotherm for which both the two states with the pressure Pe on the isotherm can be seen in the diagram. The labeling of the states along the isotherm remains the same, that is, the states B and F denote the boundary states of the phase transition, and the states C and E denote the local maximum and the local minimum of the isotherm in the pressure versus volume diagram. We introduce the point H on the upper branch of the isotherm, where the pressure of the gas is equal to the pressure in the state E at the local minimum. Similarly, the point J on the lower branch of isotherm represents the state where the pressure is equal to the pressure in the state C at the local maximum. Let us suppose that the system proceeds along the isotherm from the initial state A in the direction of the state H. For pressures less than pH, which is equal to Pe, the molar volume of the system is single-valued and unique for given pressure and temperature. This is also the case for pressures greater than Pj, which is equal to Pc, that is, a system evolving along the isotherm from the state G in the direction of the state J has a single-valued and unique volume. These branches of single state on the given isotherm lie within the green regions in the diagram. However, as the pressure increases above pH or decreases below Pj, that is, P is in the interval between pH and Pj or equivalently between Pe and Pc, three states of equal pressure become available on the isotherm. The branch representing such states of the given isotherm lies within the orange region, where any horizontal line of constant pressure will intersect the isotherm in 3 points representing the three available states for given pressure and temperature. For example, the states B, D, and F are such available states at the pressure Pb, where two of these states, namely the states B and F, are stable, and the state D is unstable. This situation can be studied in more detail if we substitute the molar volume for a given pressure and temperature into the formula obtained for the Gibbs potential, or equivalently the chemical potential, and plot the result against the pressure as the medium evolves along the isotherm from the state A to the state G. First, we do not assume that the states B and F are the boundary states of the phase transition, but some arbitrary states at some pressure Pb in the orange region of the molar volume versus pressure diagram. The graph of the free enthalpy versus pressure has 3 segments, where the first segment passes through the states A, H, and B, and stops at the state C. The second segment originates from the state C, passes through the state D, and terminates at the state E. The third segment starts at the state E and passes through the states F, J and G. As the molar volume versus pressure diagram shows, the first and the third segments are concave segments, where the partial derivative of the volume with respect to the pressure at a constant temperature is less than 0. This means that the system evolving along these segments is mechanically stable. The second segment of the graph between the states C and E is a convex segment, where the partial derivative of the volume with respect to the pressure at a constant temperature is greater than zero, and this segment therefore represents mechanically unstable states. Mechanical stability for a gas or a medium just means that its volume will shrink with increasing pressure. It will also maintain its physical properties without phase transition provided the substance has also thermodynamic stability. The green and orange colors in the second diagram representing the regions with one unique solution or three available states for the molar volume show that mechanical stability does not necessarily imply thermodynamic stability. Although the mechanically unstable segment between the states C and E completely lies within the orange region where one of the available states is unstable, the other two mechanical stable segments pass through both the green and the orange regions. They have parts where the system has thermodynamic stability, such as the part of the first segment for pressures less than pH in the green region, and the part of the third segment for pressures greater than Pj in the other green region. In the orange region both the first and the third segments are thermodynamically unstable. Any state on the convex segment, for example the state D, is unstable, but the Gibbs potential has local minima for the corresponding states B and F at the same pressure on the concave segments. Whether the system actually selects the state B or the state F depends on which of these local minima of the Gibbs potential is lower. As seen in the plot, the medium has lower free enthalpy in the state B. Thus the state B is realized as a true physical state for the given pressure and temperature. As already mentioned, we have not assumed that the states B and F are the boundary point of the fully saturated states of the medium. By imposing the Gibbs criterion on the states B and F, we demand that the system has the same free enthalpy or chemical potential in these states, and they are located at the intersection of the two concave segments. As a result, both the states B and F are selected by the criterion, that is, both of them are realized in the system as the boundary states of the phase transition of the medium. The evolution of the medium along the isotherm from the state A to the state B in the molar volume pressure diagram corresponds its evolution along the first concave segment between the states A and B in the Gibbs potential versus pressure diagram. Then the physical isotherm is constructed as an isobaric line between the states B and F while passing through the state D in the molar volume pressure diagram, which corresponds the evolution along an isobaric path between the point B on the first concave segment to the point D on the convex segment, then from the point D to the point F on the second concave segment. The evolution of the medium along the von der Waals isotherm from the state F in the direction of the state G corresponds its evolution along the second concave segment from the state F in the direction of the state G. If we want to determine the boundary states B and F of the phase transition of the medium based on the Gibbs criterion, we need to solve a system of equations as in the case of the Maxwell construction. The first equation is still the one establishing the equality of the pressure in the states B and F, and the second one is the equation imposing the equality of the Gibbs potential in those states. We need to evaluate the equation describing the change in the free enthalpy evolving from the initial state B to the state F where the left-hand side vanishes. By applying some numerical algorithm to solve this system, we can obtain the pressure and the molar volumes in the states B and F of the boundary of the phase transition. We have presented a method called Maxwell construction providing the correct description of the physical state of real gases in the unstable region of the isotherms of the von der Waals gas used as an approximation. For a given von der Waals isotherm for temperatures less than the critical temperature of the gas, we had to determine the boundary points on the isotherm that correspond to the saturated phase of the medium. We have discussed two approaches to construct a physical isotherm based on findings the boundary states of the phase transition. Both of the approaches use two criteria imposed on the boundary states formulated in mathematical equations, which can be solved by applying some numerical method. The first approach of the construction of a physical isotherm suggested by Maxwell starts with the assumption of the equality of the pressure in the boundary states, that is, the pressure of the medium must be the same in both the states. The other assumption is the equality of the areas of the two closed curves formed by the intersecting von der Waals isotherm and the isobaric physical path along which the medium evolves. The second approach applies the Gibbs criterion, and also starts with the assumption of the equality of the pressure of the medium. Instead of the rule of equal areas, the criterion demands the equality of the Gibbs potential of the medium in the boundary states. Whether we follow the first or the second approach, the solution of the mathematical equations of the assumptions used in the construction will provide the volume of gas in the boundary points of the isotherm representing the saturated phase of the medium at a given temperature, and the pressure of the medium in the process of its phase transition. As a result of the Maxwell construction, the von der Waals isotherms are replaced by broken curve isotherms with isobaric paths along which the phase transition of the medium takes place, and we obtain a family of isotherms for temperatures less than the critical temperature of the medium in its pressure versus molar volume diagram. The boundary points of the phase transition define a curve known as Maxwell curve. We already mentioned that the curve of the boundary points encloses the boundary curve of the mechanically unstable region of the isotherms, and the two curves only meet in the critical point K of the medium. The critical isotherm and the Maxwell curve represent the boundaries between the different phases of the medium, that is the different states of matter in the pressure versus volume diagram. The critical isotherm separates the green region representing the state of permanent gas from all the other states. The critical point K divides the critical isotherm and the Maxwell curve into two parts or branches. The blue area representing the liquid state of the medium is bounded by the left-hand branches of the critical isotherm and the Maxwell curve, whereas their right-hand branches form a boundary for the left-hand side of the orange region of unsaturated vapor. The yellow area under the Maxwell curve is the domain of the phase transition of the medium, where it exists in the mixed phase of liquid and saturated vapor. We note that this diagram only gives a partial information in the phase transition of real gases or substances. Here we show the so-called phase diagram, which is a pressure-volume-temperature diagram of any medium under the study of its phase transitions. We can recognize the isotherms of the medium as the intersections of the T equals constant planes with the surface displayed in the diagram, which are represented by the dashed lines. Only the critical isotherm passing through the critical point K is plotted with continuous line, which separates the domain of the state of gas represented by the green surface from the other domains of the phase diagram. We can also identify the blue, the yellow and the orange areas bounded by the critical isotherm representing the liquid vapor, and the vapor state of the medium respectively. However, the phase diagram also shows other three phases, such as the regions of the solid-liquid and liquid phase transitions represented by the red and the turquoise surfaces, and the region of the solid state represented by the purple area. This diagram will be discussed in more detail when we study the phase transitions of matter.